Good morning, all of you. In the last class, we had discussed about mean, median, mode, and fractiles, and so on. Now, we are going to discuss some of the variations. How far an observation deviate from its central value, its mean. Right. So that is a measure of variation. Right. Beyond the average. Beyond the average, understanding the dispersion in the data, right? So what is dispersion actually? For example, you are expecting that you will get a marks in a particular examination. Say uh, you expect 80 marks. Your expectation is 80 marks, but you get marks that may deviate from the expectation. Say you may get 85, 90, 95, right? Or sometime you may get 70, 75, or 60, or 55, right? So these are what? These are variations. So this is the expected value, and these are variations. How far it varies? For example, so this is the expected one, no? You get 5. So the variation is plus 5. And here 90 marks. Variation is plus 10. Here variation is plus 15. The variation. Or sometimes the variation may be in adverse. So here 70 marks, you may get minus 10 variation. Here 60 marks, you may get 20 variation. And here 50 or 55, you may get 25 variation minus. This is a variation. Likewise, uh, we should know, right? We studied the mean. Mean is a central point, right? From that central point, how a particular observations are deviates, right? For example, here, if we assume this is your mean, this is a mean, and these are the observations. Observations. If the observations are very close to this mean, then less variation. It has less variation. And if the observations are far more from their mean line, so it is high variation. Right. Now, today's session is about how do we measure this kind of variations. Beyond the average, understanding dispersion in the data. For variation, we use another term, dispersion. Right? Dispersion is variation in the data. Measure of central location like mean tell us where the data is, central location. But they do not provide an adequate description of reality. To understand the full picture, we must measure how the values spread. This is study of variation, right? Here, I can give you one more example in the class, the mathematics subject. Average marks of the students 70, right? Average marks of the student is 70. There are 50 plus students in the class, right? Then when we plot all of their marks in a sheet, then some of them are getting 72, some of them are getting 75, some of 60, right? 68, 71, 76, like that. So these values are very close to the mean. And also there are students, they may get marks 90, 95, 98, 99. So it's far more varied from the mean value. This is plus. And there are students, they may get 2 marks, 5 marks, 6 marks, 9 marks, right? 10 marks. Right? You see, these are far more varied. So from the mean, from the central value, this set of data. So this set of data and this set of data deviate far more from that mean. But here, when you look at this data set, it's very closer to the mean value, right? So that's what. Then how do we are going to measure it? Incomplete truth. Incomplete truth. When we say blindly, the average marks is 70, average mark is 70, it does not provide a detail, right? It failed to provide insights whether all of the students in the class are closer to 70 or there are some more variations among their marks. So that kind of things we have to measure. The incomplete truth, the problem with averages. What are the problems in the averages? The extent to which a set of data tend to spread, right? Tend to spread about the average value is called the variation or dispersion. As I told you earlier, how far it varies, how far it spread. You look at here. This is a mid value, a mid central location. Here, when you look at this data set and this data sets, they are far more deviate from their average. And here, these values are very close to the mean. Here it's mean less variation here, and here more variation. Here there are many more variation, right? Here. To measure variations, we may use a different kind of tools. There are toolkits, of which the range, one measure. This is the simplest and snapshots. Simplest and snapshot. So range mean from the data set, we take the minimum value and maximum value and find the differences. That's a range. So there's a difference. That's a variation. How far? The maximum and minimum. The range. Quartile deviation. We already discussed about Q1, Q2, Q3, like that. Quartile and deviation mean we take, right? This is a line. So line. This is median Q2, and this is mean Q1. This is Q3. Then we take these figures and we calculate this one and this one. Q3 minus Q1. So this gap is interquartile range. Interquartile range. But here, this is minimum value, this is maximum value. And the differences between the maximum and minimum, this is range. But here, Q3, Q1, Q3, this is interquartile range. Interquartile range. And interquartile deviation mean we take the interquartile range and we divide by 2. Then we get their quartile deviation. So this considers the middle ground. It ignores this area and this area. It covers 50% of the data set. Mean deviation, average distance from the center. We take the mean and how far a particular observations spread out, deviates from its mean, its central value. So we take the average. So this is average distance from the center, that is mean deviation. And the variance, finally, variance and standard deviation. This is the gold standard in measuring the variation, dispersion. The statistical gold standard. So this is give a much precise measure. So when you look at from this end to and this end, it gives, right, it's a continuum. The variation measure is strong, far more strong here and far more weak here. First, let's start from the range. The difference between the largest and smallest value in a set. Largest and smallest value data set. For example, we have data. When we arrange the data, it like this. Here, smallest value 36, 44, 55, like that, and the highest value is 98. To find out the range, here we know that this is the largest value and this is the smallest value. Then the difference, the range, 98 minus 36 equal 62. So this is the range. This is range. So limitation, the critic or the problem in this measure, limitation, while easy to calculate, right? It's very easy. The range is not always a good measure of variability because it is completely ignores the distribution of the data between the extremes, right? So it has a lot of things, lot of issues. So sometimes most of the data set may be plotted here, but it consider only two extremes, highest and the smallest, and and there are very few observation in this area and this area. So therefore, so it totally ignores its insights. And interquartile range, I have uh, explained in previous sessions. Interquartile range and interquartile deviation. Very simply, interquartile range mean Q3 minus Q1, and interquartile deviation means interquartile range divided by 2. This is called quartile deviation. I have shared you a PDF where we can find that example as well. And the mean deviation, accounting for everyday data points, mean deviation here. Instead of just looking at the edges, the range, right? In the previous example, we consider only two extreme values, highest value and largest value, and the minimum value, lowest value. Mean deviation, we call them as a MD, mean deviation, measures the averages of absolute differences. Here the term absolute differences between each values x and the mean. Simply we take the average x bar, average. How far a particular observations deviate from its mean. So there's a difference. So this is observation x minus x bar. So this is a deviation. And here they talk about absolute deviation. Absolute mean, here we put this mark. So this represent absolute. For example, absolute of 2, right? We write the absolute value is 2. Then it is 2. And what is the absolute value of minus 2? What's the absolute value of minus 2? Here, absolute of minus 2 is equal to, and 5 minus 5, absolute value of minus 5 is 5. So absolute value mean we are ignoring the sign of the value. Regardless of the sign, we take the full number, absolute value. Right. Mean deviation equal absolute differences from mean. This is x observation. It's a mean, the differences, and we take their absolute and we get the total, sigma, sum of all values. And it should be divided by total number of times, the number of observations. Right, here calculating the mean deviation, one group data. The data set is given to you. This is a data set. Data is not arranged in order. It's not a matter here. For quartile range, or interquartile range, or uh, quartile deviation. For that purposes, we may need to arrange the data in ascending order or descending order. But here, to calculate the mean deviation, we don't want to sort the data set. Right, here the data set 24, 32, 18, 43, 13, 15, 30, 15. And number of observation 1, 2, 3, 4, 5, 6. There are 6 observations. The first step for calculating the mean deviation is to calculate the mean. First, we have to calculate the mean of this data set. How? 24 plus 32 plus 18 plus 43 plus 30 plus 15. Then we will get 162, and number of observation is 6. So therefore, the mean is 27. Mean is 27. Right. Now we have x observations. X observation. I can write here. Here x and x minus x bar. And absolute term of x minus x bar. Right. So here I can draw. Right. The first point 24, 32, 18, 43, 30, 15. And we already calculated x bar, that is equal to 27. Then 24 minus 27, what's the value? 3. 24 minus 27, 3. And 32 minus 23 equal 5. 18 minus 27, 9. Right? But here it's negative. Right? It's negative. It's plus, it's negative. And 43 minus 27, 16. It's positive. And 30 minus 27, 3 plus. And 15 minus 27, minus 12. Minus 12. But here we take absolute. We take absolute of this value. Then absolute value is 3, 5, 9, 16, 3, 12. And then we have to take the sum of these values. So when we take together, it is 48. It is equal to 48. And according to the formula, mean deviation is this formula. Yeah, we know this value. This is 48, and the number of observation is 6. Then we will get the mean deviation is 8. Mean deviation is 8. So what does it mean? What does it mean? We found mean deviation. So what does it mean is, we know that we already calculated the mean is 27. 27. And here mean deviation is 8. So this data set, right? This data set, most of the values may range from plus or minus 8. It's mean here 27 is the mid value, and 27 plus 8, 35. And here this is value to 27 minus 8, it's equal 19. Simply the meaning of this, the data set, most of the data points lies in between 19 to 35, most of the data sets. So that's the mean. That is the meaning of this mean deviation. So this is mean and this is mean deviation. So based on this, we can conclude that most of the data sets are lies between 19 to 35. Clear? Any questions? Interpretation. What is interpretation of this? Most numbers lie between 19 and 35. How we got? This is mean and this is mean deviation. It may be plus or minus the data set. Right. Now we'll expand this mean deviation with frequency, and like fx. To calculate the mean, how do we calculate mean? Sigma fx over sigma f. So in this instances, how do we calculate mean deviation? Here the data set is given, the numbers are given to you. 5, it occurs 2 times. 7, it occurs 1 time. Likewise, the data is given. Here the frequency, the sum of frequencies mean number of observation is equal to what? 11. And here fx frequency into x. Here 5 into 2, 10. 7 into 1, 7. 8 into 3, 24. Likewise, we take fx. Why do we need to find out the fx? So we know that this is the x value, x bar equals sigma fx over sigma f. We need to find out x minus x bar and absolute term, right? So the n divided by number of observations. The number of observation equal to sigma f. So this is sigma x minus x bar. So that first step number 1, we have to calculate the mean x bar. So x bar sigma fx over sigma f. Right. Now we calculate sigma f. How to calculate sigma f? Here we already calculate fx. Then the total of this fx 88 and sigma f 11. So therefore the mean is equal to 8. Mean is equal to 8. Right. Now we know that x bar equal 8. And this is an observation. This is our observation. X minus x bar. X minus x bar. That is what? X is 5. X bar is 8. Then deviation is 3. Deviation is minus 3. But here we are considering only the absolute term. Absolute term mean here we don't want to consider the sign, right? The sign is not a matter. Likewise, 7 minus 8, 1. 8 minus 8, 0. 9 minus 8, 1. 11 minus 8, 3. So this is absolute deviation. Since we are using the frequency, then this value should be multiplied by the frequency. It's mean 2. So 2 times it deviates. 3 deviates 2 times. 1 deviates 1 time. 0 deviates 3 times. 1 deviate 4 times. Likewise, here 2 into 3, 6. 1 into 1, 1. 3 into 0, 0. 4 into 1, 4. 1 into 3, 3. So therefore, here we get the sigma x minus x bar absolute term. It's called 14. Right? Sum of deviation equal 14 and the mean deviation equal, right, sum of deviation divided by number of observations. sum of deviation 14 and the number of observation that is equal to sigma f 11. So therefore the deviation, mean deviation is 1.27. So how can we write this to interpret this? We know that mean is 8, and the deviation is 1.27 plus or minus. Then it range is what? Range is 6.67, 6.83, 6.6, sorry, 6.73 or something to 9.27, the range, right? So this is how we calculate mean deviation with frequencies. Clear? Any questions? Now we move to the most important area, the gold standard for calculating variations. So those are variance and standard deviation. These are the gold standards. So why it is better? So when we calculate the mean deviation, right, mean deviations, for example, this is the mean, this is a central value. Here, if it deviates from this side, it's plus 3. And if it deviates from this side, it's minus 3. Now, we ignore the sign. We ignore the sign. Here, we take 3 and 3, right? Because we take absolute term. Rather than ignoring the sign of the deviation, the differences, mathematically, we do like this. If the difference is 3, no, the difference is 3. Then 3 square and minus 3 square and 3 square. Then it's automatically become 9. Is 9 plus 9. And here also 9. So it is mathematically removes the sign. Mathematically remove the negative sign. The squaring penalizes outliers more heavily. Outliers mean extreme values more heavily and remove negative signs mathematically. So that's why we use. So here in the mean deviation we use linear distance, but in variance in standard deviation, we get the square, right? X minus x bar square. Here in the mean deviation, we take this value, x minus x bar. And so this is for mean deviation. And for variance and standard deviation, we take x minus x bar and we take the square. So here also we get a positive value. Here also we get positive value. But the thing is, mathematically, this is strong. Mathematically removes their sign, and the research said the square, right? Squaring the differences work fine in the extreme data sets, extreme variations. Right. Definition of the variance. There are terms, right? S and S here. S normally we use for the sample standard deviation. This is sample standard deviation. And if you put S square, standard deviation square, it's called variance. Right? Variance normally we put S square, right? Variance mean S square. This one, sample variance. The average of squared variance, squared deviation, that is what variance. Variance means the average of squared deviation. Here, this is the deviation. No, this is a deviation. This is deviation, and we make it square. We make it square and n minus 1. Then we get s square. S square variance. S square. And if we find the square root of this, if we find the square root of this, it's become standard deviation. The square root of the variance, right? Yes, right? Yeah, this is variance, no? This is variance. And the square root of this variance is equal s. This s is standard deviation. Simply people say the square root of the variance is equal to standard deviation. Here x minus x bar and square and divided by n minus 1. Then we take the square root, then is equal to uh, standard deviation, right? And here you may notice n minus 1, the mean deviation we use only n, not n minus 1 in the denominator part. So this is called, right, sample, right? So there are two measures of variations: sample and population. Sample and population, and variance and standard deviation. There are notations, right? So notation for sample variance we put s square, and standard deviation we put s. For population standard deviation we use this notation. We use this notation sigma, and for population variance we use this, right?